Hello YouTube, this is my second video that I'm making in my module on binomial experiments or binomial probability distributions. And in the last video we kind of confronted what do we consider to be a binomial experiment. It'd be an experiment where we could reduce it to, say, two possible outcomes. We say successes and failures. But we also kind of explored this formula right here. And in this video we're going to focus on using this formula again, but kind of knowing the formula is great, but also using a table that we often associate with the binomial experiments because we get into larger sample sizes or larger number of trials. So recall that a binomial experiment is any experiment in which we can reduce the outcomes to being either a success or a failure. And it's given by this. We say if x represents the number of successes in n trials of this experiment, then the probability of x successes is given by this formula right here. Okay, so you'll notice that the values we need to be familiar with are n, which is the number of trials, x, which is the number of successes in that number of trials, and then lowercase p and q represent respectively the probability that we get a success or probability we get a failure. So let's go ahead and put this to use in this example here, example number 2. But it says, consider this situation. A survey found that 1 out of 5 Americans, so we have 1 out of 5 Americans, says he or she has visited a doctor in any given month. It says if 10 people are selected at random, find the probability that exactly 3 will have visited a doctor in the last month. Okay, so in this instance, the first thing we want to do is we want to write out what constitutes a success and what constitutes a failure. And so since the probability I'm being asked to find here is this, find the probability that exactly 3 will have gone to the doctor, then we'll write this. We say success, and we write this off to the side here, equals went to doctor. Went to the doctor will represent a success. So if that's a success, then anything but going to the doctor would be a failure. So we just say no doctor, and we'll just keep it simple like that. But we say this is what constitutes a success and a failure. Furthermore, in this experiment, we say, well, what probability are we trying to find? Well, the probability that exactly 3 will have visited the doctor in the last month. So in other words, the probability of getting x successes or the probability of getting 3 who went to the doctor, where this is our x, okay? So here's what we know about this experiment. We say, well, how many trials are there? We say, well, 10 people are selected at random. We're going to have that represent the size of our sample, or at least the number of trials we're running, each person. And then we say, okay, well, the number of successes we have here is 3. So here's where P and Q come into play. We say, well, P represents the likelihood that we get a success. Now, the probability we get a success is the probability that somebody actually took the time to go to the doctor, and we were actually told this in the problem. We say 1 out of 5. So this is a 1 in 5 chance, or we could represent this as a decimal as 0.20. So the nice thing about knowing the probability of getting success is 1 out of 5, well, then probability of getting a failure would be the other 4 out of 5, or the other 80%. But now that we have these values, we can just go ahead and simply put them into our formula. So the formula, recall, looks like this. We say the number of, trials is on top. We say we had 10 total trials. Let's start with this. How many successes do we want here? And in this case, we want 3. So in the basement, we have 3 factorial. So if we had 3 successes, then how many failures out of the 10 would there be? Well, that'd be the other 7. Okay, and you can see that this goes with the formula up here. We say x factorial times n minus x factorial, where n is 10 and x is 3. This would be 10 minus 3 factorials, or 7 factorial. So we get what we have here in this expression. Now, the next thing we need to put up here are these values. We say p and q to these powers. We have p and q, and we already know p. I'm going to put it in as a decimal, as a matter of fact. We say 0.20, so this is our 0.80 probability of failure. And the nice thing about this is if we already know the successes, and we already know the number of failures, which is n minus x, we can just transplant these numbers up here. So in other words, we just put the 3, which is the number of successes, on the probability of getting a success. And we'll put 7, which is the number of failures, on top of the probability we get a failure. As a matter of fact, this is the answer right here. What we get to do now in this instance is simplify this. And you're going to find out that this is not a very desirable situation. That is, if I were to simplify it, I'd say it's 10 times 9 times 8 times 7 factorial over 7 factorial, 3 factorial. Or actually, let me put it in the order I have it written on the left over here. 3 factorial, 7 factorial, where the 7's kick out. And then we have this 0.20 to the third, 0.80, yikes, to the 7th power. So here's what we end up with. We have 10 times 9 times 8 over 3 times 2 times 1 times these decimals to their respective powers. And what you can see, I hope, is this. Using the formula, actually we can be accurate with this. We can reduce our 3 and our 9 here, make this a 3. Reduce our 2 and say our 10 here, make this a 5. 5 times 3 is 15. 15 times 8, be the same thing as 4 times 30. So we have 120 times 0.20 to the third times 0.80 to the seventh. But as I was saying, you can see how using this formula is not very desirable, because now I get to get out a calculator and type all this in. And we'll talk about how we can avoid using the formula here in just a moment. So we say, all right, how about we do this 0.2 to the power of 3 times, now in parentheses, let's put 0.8 to the power of 7 in parenthesis. So I've multiplied these two decimal values. Now we'll take this times 120. So we get about 0.201, okay, ish. So the probability of 3 successes is approximately 0.201, which is approximately 20.1%. Okay, so before we go ahead and show how we could have done this otherwise in a quicker fashion, I do want to kind of talk about the reasonability of this. We're saying, all right, well, it's about a 20% chance that, you get somebody that goes to the doctor, randomly in a given month. So if I had 10 people, we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would expect that maybe like 2 of them, went to the doctor, and the rest of them, are failures. But we say, how likely is it then that that we get 3 people that have been to the doctor, and we got about a 20% chance, ish. So not bad. So how could we have done this otherwise? Well, the nice thing is, or the not so nice thing is, when you use the formula, you can see how these numbers, they can kind of be a pain in the rear. Okay, but the nice thing is, if we actually know these values right here on the left, we know the number of trials, we know the number of successes that we have, and let's just put it this way, in the probability of success, we know that too. I don't really have to tell you the probability of failure, because if I know the probability of success, say, is 20%, then everything else is a failure, the other 80%. But if I know these top 3 values here, we actually have a table, and this is usually in the back of textbooks. I actually just got on Google and and searched binomial distribution tables, and I was able to find this here. And what you see is this giant table full of probabilities, and the way it's organized is this. So you'll notice, first of all, on the left here we have a column, and you see n. So n represents the number of trials we have. So for example, we say 2 trials, 3 trials, 4, 5, 6, 7. I'm going to go down a page, because we were dealing with an experiment which we had 10 total trials. Okay, and you notice they have an R here. If I go back up to the main page here, you see the formula up here. It says n choose R. We have n choose X. So R and X, they're the same thing, where in this case R and X, X represents the number of successes out of the n total trials. So we're going to represent it on this table as R. But basically, you'll notice here for our 10, we say, well, if I had 10 total trials, you'll notice that R, or X, number of successes, starts at 0 and goes all the way up to 10. You notice it doesn't go past 10. And the reason why is because you can't have more successes than you had trials. Or in the case of, if we selected 10 people at random, you can't say how likely is it that, say, 11 people went to the doctor. You only had 10 to begin with. So you'll notice that each subsection here, like for example, a sample size 9, or 9 trials, it'll go from 0 up to 9, or 8 trials, it'll go from 0 up to 8. But this R column, or we say X in our instance, represents the number of successes. And then you'll notice that at the top here it says P. So P, recall, P represents the probability of getting a success in the first place. And you'll notice that they have different increments here, like a 1% probability of success, 5, 10, 15, 20, all the way up to 95% probability of success. But we actually could have used this table to determine the value we were looking for. So for instance, in our case, we wanted the probability of exactly 3 successes. And we'd write it like this. We'd say probability 3 successes. Okay. But what we knew is this. We had a sample of size 10. We had an X, or in this case, when we read the table, an R value of 3 successes here. And we know the probability of success is 0.20. If we had known these 3 things, we could have just come over to this table here. So let's take a look at this. We say we have a sample of size 10, or 10 trials. We have number of successes is 3. So here I am in this 3 column here. Let's see if I can highlight this 3 right here. And we go up to the top, we say 20% probability of success. So if I trace this down, and, we trace it over 3 successes runs into 20% success rate. Let's see if there it is, 0.201, and that is exactly the same value we had gotten by using the formula in the first place. So, if you're asking me, well, which way would I prefer? If we had a small number of trials, we might use the formula, but geez, look at this formula. It's not very desirable to use in an instance where, oh, okay, well, we could just use a table. So that table being revealed to us here, let's look at a different thought experiment. In which we'll use the table instead of the formula, even though we could use the formula. So we say, consider the following situation. A public opinion poll was conducted and found that 5% of Americans are afraid of being alone in a house at night. So we say if a random sample of 20 Americans, so that's our sample size or number of trials, is selected, find the probabilities using the binomial table. So this time we don't want to use the formula, we want to use the table. Okay, so let's write down what we know instantly. First of all, we know that we have 20 trials. That's 20 people in our sample. Each person constitutes a trial of the experiment. We say 5% of the Americans are afraid of being home alone at night. If we read this first instance here, we say, all right, find the probability that there are exactly 5 people in the sample who are afraid of being alone at night. Since I care about people who are afraid, the first thing I'm going to do is I'm going to say a success. What constitutes a success? Success is afraid. You know, we're talking about people who are afraid. So we say failure. Failure would be people who's not afraid. Anything but afraid when they're at home alone at night. Oops. So let's switch colors here. Nope. Try again. Try again. There we go. So we have success and failure defined. Essentially we say, well, the number of things we have is 20. And we say the probability of getting a success, well, it's a 5% chance that they're afraid at night. So 0.05. So this is going to be true for all these probabilities that we find here, but we say find the probability that exactly 5 people are afraid. We say in this case we want 5 successes. So we're going to write down the probability we want. Probability of 5 people scared out of 20. And we're just going to go look this up in the table. So we say, all right, looking at my table, we say we need a sample of size 20. Let me flip down a page here, flip down another page. So here's our sample of size 20. And we say we wanted exactly 5 successes. So we'll go down here, we say 5. There's my 5 right there. And we're going to trace this over to now the 5% column for probability of success. So we say our 5% column, if I trace this down, we see that we run into each other right here at 0.002. So we say the probability of this is approximately, we'll put approximately 0.02 or about a 2% chance. Okay, and you know, thinking about this, think about this. If, you know, 5% of people are afraid at night, you know, if you had 20 people, how likely is it that 5 people out of the 20 would be afraid? That's like saying 5 out of 20 people. That's like saying 25% of the people would be scared. Well, we only expect about, you know, 5% of them to be scared. So how likely is it that we get 5 people that are scared, you know, out of 20? It's not likely that a fourth of our sample is going to be scared if there's only a 5% chance that they're scared in the first place. So it's reasonably sensible that we get only a 2% chance. Okay. So now we're going to play a little word play here. We say there are at most 3 people in the sample who are afraid of being alone at night. We still have 20 people in our sample, or 20 trials, and we still have a 5% probability of success. It's just that in this case we say at most 3 people are going to be afraid. In this case we don't say x equals 3. We're going to say at most really means this, less than or equal to 3. You know, if I were to write this out, we say probability of less than or equal to 3, and this is what I would want to see if I had my students writing it. We say probability less than or equal to 3. Keep in mind that this means probability of 0, or the probability of 1, or the probability of 2, or the probability of 3. So in this instance, what we have to do is we have to go look up each of these in the table. And when we look at this table, we say, well, I still have a sample of size 20. I'm still in this 5% column. But when we say 3 or less, here's our 3 right here. We say 3 or less, we're really referring to, let me get my calculator out here. And we'll drag it over here. We say it's this 0.06. We say 0.060 plus, now this 0.189 plus 0.377 plus 0.358, and we get this right here. And I think that I can pull out a tape here. Let's see. Yes, I can. So going back over to our experiment here, and I'll get my tape back out. Basically, we said, all right, we had 0.060 for our 3 here, 0.060. Let me see if I can find this again. We have 0.189, so 0.189 for this guy. Again, we had 0.377 for this one, 0.377. Write this a little bit cleaner. And then last but not least, we had 0.358, so 0.358. We can add all these together, and when we did so, we got about a 0.984 chance. Oops. 0.984, I accidentally erased it, or a 98.4% chance. And again, let's talk about the reasonability of this. If only 5% of the people we would expect to be scared, how likely is it that it's going to be, you know, less than 3 people out of 20 people? It's a pretty good chance that, you know, less than 3 people will be scared if only 5% of the 20 people are supposed to be scared, okay? So keep in mind when we say less than or equal to 3, all we'll do is we'll go over to this table and we'll sum all these up right here. Okay, so here comes the kicker. This last one, we say find the probability that at least 3 people in the sample will be afraid alone at night. So we say probability of greater than or equal to 3 people. So here's the unfortunate thing about this, and I could write it all out. We could say, well, probability of greater than or equal to 3 people, that'd be 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Do I really want to go over to my table and say 3 or more and add up 0.060 and everything below this? You notice that they start to drop out after a while. But the thing is this, you might say, well, all I'd have to do is add the 0.060 plus the 0.013, which represents 4 successes, and the 0.002, which represents 5 successes. And all of these are so negligibly small that we could just leave them out. Couldn't I just do that? And the thing is this, we don't want to do that because actually it's not precise. All those 0.000s, they are very small, but when you add them together, they do actually add up to stuff. So when you find something like this, what we're going to do instead is use the complement. And what we mean by the complement is we're going to say this: why don't we just take 100% of our stuff and subtract off the probability that it's less than 3? In other words, everything but this. So to look at our table, essentially if we said 3 or more, what we could do instead is we could take this entire column and subtract off the probability of 0, 1, or 2 successes, because that gets rid of the ones we don't want and leaves behind what we do want. So we say 0, 1, or 2 successes. I know what those are. I've got those written right here, 0, 1, or 2. So what we'll do instead is this. We say it's 1 minus this, let's see, 0.358 plus 0.377 plus 0.189. We could just take those off. So getting the calculator back out here, get this out of the way here, we could say, all right, well, first things first, let's do this 0.358 plus 0.377 plus 0.189. We could just say it's 1 minus 0.924. So we have 1 minus 0.924, which comes out to be this. I'll just subtract 1 from this, and then we'll flip its sign back. But 0.076, so 0.076, or about a 7.6% chance. So, again, if 5% of your, number of trials here is what we expect to be scared, and we have 20 people, 5% of 20, by the way, is only 1 person. We're saying, well, how likely is it that we get 3 or more people who are scared? It's not a very good chance, because you wouldn't expect that many. You only expect 1 out of the 20. So 3 or more is not very likely to occur. So this is a good, kind of review of how you would use the formula, but also how you could use the table to look up these probabilities. Cheers.